Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
The elementary particles are those particles that are the basic building blocks out of which everything else is built. We commonly hear that atoms are the basic building blocks of all matter, and we've learned about the periodic table ever since Mendeleev. And it's true that atoms are the basis for chemical structures, but it must be recognized that they themselves are composite objects. Atoms are small, and the things that make them up, their constituents, are even smaller. These facts are that these objects are so small makes it really challenging to use some of the units that we're commonly used to in the MKS system, as we'll show now. What are the elementary particles? Well, if we think about a human hair as being 100 micrometers in size and various bacteria being on the order of single micrometers in size, think about the fact that an atom is on the order of an angstrom, or a tenth of a nanometer in size. A nucleus within the atom is literally 4 orders of magnitude smaller than that. It is on the order of 10 to the minus 14 meters in size. A nucleus is made of objects itself. It's not a fundamental object. It's divisible. It's made of protons and neutrons. The proton and neutron are each on the order of 10 to the minus 15 meters in size. And the proton is also not a fundamental object. The proton and the neutron both are thought to be made of quarks. Quarks are currently thought to be fundamental particles, and within our limits of measurement, they are shown to be less than 10 to the minus 18 meters in size. They may be divisible further, but no apparatus has been constructed such that they can be proven to be so. Thus, we include them in our family of fundamental or elementary particles. The other constituents of the atom are the electrons, which orbit outside the nucleus. These electrons are also thought to be fundamental. And it is thought that if they have a radius, that radius is much smaller than 10 to the minus 18 meters. If you can think about the scales that we're talking about here, there are literally 8 orders of magnitude between the atom and the electron. And so even though we might be willing to tolerate dealing with scientific notation in 10 to the minus 10 meters when discussing the atom itself, it's a tenth of a billionth, it gets to be somewhat cumbersome to start talking about 10 to the minus 18 meters on a routine basis. And in fact, we don't do this in atomic physics, even at the 10 to the minus 10. We invent the scale of the angstrom, defined to be 10 to the minus 10 meters. When we consider further what are all the elementary particles, there are thought to be 12. 6 of them fall into the category of quarks. 6 of them fall into the category of leptons. The difference between these two is that the upper set, the quarks, can feel one of the forces called the strong force, and the lower set cannot. In addition to these 12 fundamental particles that make up everything else, are 4 particles that describe how forces interact between matter. So these are called force carrier particles. And it is conjectured that there's yet one more particle, the Higgs particle, which gives all the other particles their mass. If we consider the quarks come in pairs. Most of the objects we see in nature today are made of the first 2. The other 4 are heavier and thought to have decayed away in the 14 billion years since the early universe began. What's interesting about the quarks is that they fall into 2 categories. The upper row all has a charge that is a multiple of the electron charge, but it is a fractional multiple. It's plus 2/3 e, where e is 1.6 times 10 to the minus 19 coulombs. The lower row, interestingly enough, all has minus 1/3 e for the electron charge. So the lower row all has the same sign of charge as is the electron, but only 1/3 as much. In terms of mass, the first three quarks discovered, the U and the D and the S, are all relatively light. In units that we'll talk about soon, the U and the D are each about 30 mega electron volts in mass. The S quark is thought to be a little bit heavier, on the order of 100 MeV. The charm quark, discovered in 1974, was found to have a mass 15 times larger than the strange quark, or about 1500 MeV. The bottom quark, discovered in 1977, has a mass on the order of 5000 MeV. And the top quark, discovered first in 1994, has a mass on the order of 175,000 MeV, or 175 giga electron volts. That makes it have a mass of on the order of a gold nucleus, but this list of particles are all fundamental. They're all point-like as far as we know, and so that makes them quite different than a gold nucleus, in that it's a perfect mathematical point. And to think of the same mass concentrated in a top quark as is concentrated in a big ball like the gold nucleus is quite surprising. Notice the trend that on this chart, mass seems to be increasing to the right. In the early universe, all of these quarks were thought to be present, but the heavier ones have had the opportunity, because of their bigger mass, to decay into the lighter ones. So we're left today with only the far left column, the ups and the downs, remaining. The term quark was borrowed by its inventor, Murray Gell-Mann, from reading Joyce's Finnegan's Wake. It's a funny term, but we still use it. And the names of all the quarks have an equally funny connotation to them. Early names for the quarks were the up and the down, and charm and strange, and truth and beauty, but somehow, as physicists became enamored with the names charm and strange, they found equally strange, odd names for what now we call the top and the bottom. There's really no good reason for these names, just names that stuck in the end. The other category of particles are those that do not feel the strong force. These are called the leptons. One of them is quite familiar to us, and that's the electron. It appears in the far upper left of this table. The others in this upper row, the muon and the tau, are all essentially identical to the electron in that they're leptons that don't feel a strong force. And if we again think about electric charge, all of these things in the top row have a value of charge equal to -1 e, or in other words, the same charge as the actual electron, minus 1.6 times 10 to the minus 19 coulombs. The lower row of particles, the neutrinos, all have a value of charge of 0. The electron has a mass, in units we'll discuss soon, of about 0.5 MeV. The muon, considerably heavier, so it's similar to the electron in many of its properties except for its mass. It weighs 106 MeV, and the tau weighs 1780 MeV. The electron neutrino and the two other neutrinos are all thought to be essentially massless. Actually, today we know they're not exactly massless, but for good approximation, they're all 0 MeVs. These other two neutrinos that appear beneath the muon and the tau also get a subscript, and instead of being called the electron neutrino, this is called the muon neutrino, so we often put a little sub-mu right here next to this middle column, and we put often a subscript tau to refer to the third neutrino. Notice again, at least amongst the charged leptons, mass is increasing to the right. And again, all of these particles, the muons and the taus, were present in the early universe, except being heavier, they had the opportunity to decay and decay into lighter particles, the things to the further left on the table. So today we have mostly the electron and its neutrino in nature. Just to give you a sense of how we construct larger objects out of these elementary point-like objects, the proton, which has a +1 charge, is made up of 3 quarks. Two of them are up quarks, which have charge plus 2/3 electron charge, and one of them is a down, a minus 1/3 times the electron charge, which gives it its overall plus 1 charge for the proton. The neutron, which has a charge of 0, is made up of 2 down quarks and 1 up. Similarly, all other composite objects which are made of quarks can be found to be some combinations of ups and downs and charms and stranges and tops and
A
bottoms.
film disc containing 2 parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantum lasers.
What are the elementary particles? Well, if we think about a human hair as being 100 micrometers in size, and various bacteria being on the order of single micrometers in size, think about the fact that an atom is on the order of an angstrom, or a tenth of a nanometer in size.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through
Structures, but it must be recognized that they themselves are composite objects. Atoms are small, and the things that make them up, their constituents, are even smaller. These facts are that these objects are so small makes it really challenging to use some of the units that we're commonly used to in the MKS system, as we'll show now.
Laserpointers.com.
The elementary particles are those particles that are the basic building blocks out of which everything else is built. We commonly hear that atoms are the basic building blocks of all matter, and we've learned about the periodic table ever since Mendeleev. And it's true that atoms are the basis for chemical structure.